This year marked a significant history as many motorcycle brands are releasing more refined motorcycles than ever. Each has its own offering to satisfy the demands of consumers. Just a couple of months ago, Honda announced the release of 2023 Dio. Motorstar also announced the release of all-new Easy Ride 150 Fi. The thing is, many potential buyers are hyped by this news. One thing shines about this new models compared to their predecessors. Guess what? You're right, they are now fuel injected. Because fuel injection offer more fuel economy and performance. So consumers are likely to be interested in new models that offer fuel injection as standard or optional. But what exactly is fuel injection? How it works? Why is it replacing the good old carburetor that is more simple, robust, and easy to fix? In today's video we will be talking about what is the essence of fuel injection system of a regular motorcycle. How it works, what are the key components, and why manufacturers are making the switch. Stay tuned guys, and after watching the video you will understand the key components and working principle of fuel injection system of a motorcycle. First of all, before we dive into technical aspects, let's find out why fuel injection is replacing the good old carburetor. One of the main objectives a manufacturer will make a switch from carburetor to fuel injection is the fact that fuel-injected engines are more efficient. With today's rocketing price of fuel, consumers are looking for a motorcycle that can give the highest possible mileage per liter of gasoline. Another aspect is fuel injection offer less maintenance as it can tune itself to various conditions. But probably the biggest reason out there is the ever stricter emission standards. Clean Air Act is focusing the carbon-fueled vehicles to limit their contribution to the global air pollution. And the only way to make it happen is to out a computer in a vehicle to manage the fueling and lessen the pollution it creates while giving the consumer better driving experience and fuel economy. Now, how does the fuel injection works? Let's look at the key components. ECU, or Engine Control Unit. This is the heart of the fuel injection system. Sometimes called computer box, the ECU controls how much fuel is injected to the engine in a given situation. For example, during cold starts or during acceleration or during coasting on a highway. The ECU also control the spark timing of the spark plug and the pumping speed of the fuel pump. Fuel pump. The fuel pump is responsible for creating enough fuel pressure to the injector so that it can spray a fine mist of fuel into the cylinder. In most cases the fuel pump is located inside the fuel tank, submerged in fuel to keep it cool, and it also incorporates the fuel send unit that signal the level of fuel inside the tank. Injector. The injector is what the name suggests, the one responsible for injecting fuel into the combustion chamber. Most motorcycle features a port injection, meaning the injector is located in the intake manifold, but some modern cars are direct injection. This means the injector is located directly into the combustion chamber. The fuel injection system works by reading data from various sensors and calculating how much fuel must be delivered based on the signal given by the sensors. Let's have a look at each one of these sensors. Throttle position sensor. This sensor tells the ECU how much throttle is applied by the rider. The sensor is a variable resistor type that is attached to the butterfly valve of the throttle body. As the rider applies throttle, the resistor turns with the valve, giving a range of resistance value, thus altering the voltage output that is sent to the ECU. Oxygen sensor, or lambda sensor. This sensor is located at the exhaust pipe just after the exhaust manifold. Although it is called oxygen sensor, it doesn't sense oxygen concentration. It detects oxygen difference between exhaust gas and ambient air. By doing this it can tell the ECU whether the system is running lean or rich. Crank position sensor. This sensor tells the system where exactly is top dead center. It is the position in which the pistons is at the topmost position and ready to go downward. It also tells the system the revolution per minute of the crank. The sensor is a Hall effect type, which it generates a constant voltage until a dent is passed to its tip, changing the voltage abruptly. The frequency of the voltage abruption determines the speed of the crank. Coolant temperature sensor. In some air-cooled motorcycle, oil temperature sensor is used instead. The same principle, it measures the temperature of the engine so that the system knows if the engine is cooled, warmed up, or overheating. Now, this additional sensors are found in more high-end and more expensive bikes like big bikes and EYTVs. MAP sensor. This measure the manifold absolute pressure. IAT sensor, or intake air sensor. Just like the coolant temperature sensor, only it measures the air inside the intake manifold. Camshaft position sensor works in conjunction with crank position sensor to provide much more detailed data regarding engine rotation, timing and speed. MAF sensor, or mass airflow sensor. This sensor tells the ECU how much air is going to the intake manifold. For the sake of this video, we'll focus on the simple fuel injection layout used in many commuter motorcycle or scooters. The additional sensors I've mentioned are just there to provide more accurate fuel delivery on more powerful bikes, but a typical single-cylinder bike can work fine the primary components. Now let's have a look at the ECU. The ECU is basically a computer that manages the fuel delivery based on the data it gathered on the sensors. Just like a regular computer, the ECU has several working modes. First is the boot up mode. This is the first mode the ECU performs the moment it received an electrical supply. This is the moment you turn on the key. In this mode, the ECU performs a self-diagnostic test to ensure that the sensors are all working. If it detects a failure in one of the sensors, it will display a check engine light in the console. That's when you know it's time have the bike has problem and have it checked by a mechanic. Remember, the ECU only perform diagnostic test during startup, so when a sensor failed while the engine is running, it cannot be detected until you turn the bike off and on again. Boot up mode only lasts 3 to 5 seconds and then it goes on standby. Cold start mode. When engine is fired with the electric starter or by kickstart, the moment the ECU detected movement in the crank position sensor, and the coolant temperature sensor says the engine is cold, the ECU goes into cold start mode. The ECU will deliver more fuel than ideal to make sure the engine will not starve of fuel. Because when engine is cold, the fuel vapor will condense into the walls of the intake manifold, resulting to much less fuel reaching into the cylinder. That is why in older carbureted motorcycles, a choke is applied to deliver more fuel during cold start. This mode can last from 3 seconds up to 10 seconds in extreme conditions. When the engine is running steadily at idle, the ECU now switch to what is called loop mode. Loop mode is the normal operating mode of the ECU. In loop mode, the ECU constantly switches in one of two programmed operating instructions encoded into the ECU software: closed loop and open loop. In a closed loop, the ECU is reading the data provided by the oxygen sensor to obtain the correct amount of fuel. Based on how much oxygen is present in the exhaust gases, the system knows exactly if the fuel delivery is lean or rich. It adjusts automatically to provide the optimal air and fuel ratio called stoichiometric ratio. However, some manufacturers program the ECU to deliver a slightly lean mixture to obtain much cleaner emissions. ECU switch to closed loop in this following conditions. 1. Throttle position sensor is at off position, meaning the engine is at idle. 2. Throttle position sensor is at off position but the crank position sensor is reading a high RPM, meaning there's a negative torque or engine braking. 3. Throttle position sensor is open and the RPM is relevant to the current throttle position, meaning the engine is coasting or cruising. Now let's talk about open loop. In open loop, the engine does not listen to what the oxygen sensor is saying. Open loop is operating via a predetermined fuel delivery measurement depending on how much throttle is opened and how fast the crank is spinning. By gathering this two data only, the system knows how much engine load is present. The fueling is done via specific table called fuel map. Think of fuel map as an imaginary multiplication table at the back of your notebook in your grade school days. There are two axes. The y-axis represent the engine speed in r.p.m. The x-axis represent the throttle opening. By combining the two data from x and y-axis, the ECU can tell how much engine load there is by looking where the two axes meet. The point where these two axes meet is called target value. Then the ECU can deliver correct amount of fuel depending on the load of the engine. ECU goes to open loop when 1. Signal from the throttle position sensor is rapidly increasing, meaning the rider is accelerating the bike. 2. The throttle is opened but the RPM is lower than it should be, meaning the engine is under load, like climbing a steep or pulling heavy load. Since open loop is only activated at high engine load, the system immediately switches back to closed loop when it detects lower demands in power. In some cases, when the engine temperature sensor reading is high, the system switched to startup mode where it richens the fuel-to-air ratio, as we know that fuel also is a coolant in the combustion chamber. To further understand how the system works as a whole, let's create a real-world driving scenario. First thing you do is turn the ignition key to on position. This powers up the ECU with 12 volts DC. Then the ECU performs a self-diagnostic test. You will notice that all warning lights on the dashboard will light up, including the check engine light. The tachometer will sweep to maximum value and return to zero as a way of calibration. Then you will push the starter button. The ECU detected movement in the crankshaft and starts injecting fuel. But since the engine is cold, as the coolant temperature sensor reads only 30 degrees Celsius, the ECU quickly goes to cold start mode. It injects more fuel than is needed to compensate the fuel condensation through the intake manifold walls. Then the engine fires up and running steadily at idle. With the combustion chamber in operation, the temperature rises rapidly to over 70 degrees Celsius. This is the normal engine temperature. Depending on the type of engine, it plays around up to 95 to 105 degrees Celsius before the system identifies it as overheating. Then the system proceeds to closed-loop mode. Watching constantly into the reading given by the oxygen sensor, the system maintains an ideal air-to-fuel ratio. Even if you blip the throttle, the RPM rises rapidly and the ECU knows there is minimal engine load. It stays in closed loop. Now, you shift to gear to start moving. On a scooter, you open the throttle enough to engage the clutch enough to start the bike to move. The engine must overcome the stationary force in order to start moving the bike forward. The ECU sees a significant opening in the throttle but lower RPM response, therefore the engine is under load. The system now switched to open loop. The ECU looks at the fuel map table to see how much fuel must be delivered in current throttle position and engine RPM. Then it commands the injector to spray the ideal amount of fuel for the current engine load situation. The bike now accelerates as it received enough fuel. It accelerates further until the rider decides to ease off the throttle. The ECU sees this as the throttle opening is getting closer to the ideal RPM value. Now the system goes back to closed loop. The process is executed in a discrete and very quick manner. The rider won't even notice what's going on. Switching from closed to open loop is done in milliseconds and executed as many times as required. In some intricate and complex systems, like those found in superbikes and cars, some additional sensors are employed. For example, the MAP sensor, intake air temperature sensor, and MOF sensor works in conjunction with the throttle position sensor to give much more detailed information on power demand compared to ambient air pressure or elevation, giving the system ability to calculate fuel compensation in regards to elevation. Camshaft position sensor also works with the crankshaft position sensor to obtain enough data to let the ECU know when to precisely inject fuel according to which cylinder is at the power stroke in case of multi-cylinder engine. But at its core, the system still runs the same as in normal and simpler setups. I hope you have learned something while watching the video. Please leave a like and consider subscribing to my channel for more videos like this. Thank you.